Hello everybody, welcome back to another discussion in dynamics. Here is plan for today. Today we will finish this chapter. Namely, we will finish kinematics of particles. And maybe actually before talking about everything that will happen today, let us look at the right-hand side of the screen. Because I know that sometimes students like to look, they like to know what is the course content, yeah? So in this course, we offer you 8 different chapters, okay? Namely, we offer kinematics, kinetics, work energy, and momentum of particles. This is first part of the semester. And then we will repeat exactly the same topics for rigid bodies, okay? I know that sometimes students like to know where we are on the timeline, okay? And today we will just finish this chapter. And the last part of this chapter are kinematic constraints, right? So today we will just focus on inextensible rope and its applications to pulley structures, to pulley systems, okay? But I also know that you learned about more kinematic constraints, right? Ground, for example, ground or incline, it does not allow us to have a motion perpendicular to the ground or incline, right? I think that even Professor Zin did yesterday such example, yeah, where there was a ground constraint and also inextensible rope constraint, right? What else did you know? Probably, what else did you learn? I think in statics you learned like about pin, yeah, that the body is pinned and can only rotate about that pin. Yes, I believe so. Correct me if I'm wrong, I don't know, yeah. Also, sometimes body can be fixed, yeah, like body can be like welded to the, like a balcony, yeah. Balcony does not move, like hopefully, yeah. Balcony is like welded to the wall, yeah. So it's like fixed constraint, yeah. There are many others. So you probably know about more of them than I do. Okay. So anyway, today we'll talk about inextensible rope. We will do example number 1, and then we'll start a new chapter. Okay, we will start kinetics of particles. And we will do brief lecture review. Why not? And then example number 2. And if time allows, we will talk a little bit about the quiz 1. Okay, we will see how I would solve quiz 1. Sounds like a plan? Yep. Let's do it. Okay, so let's do example number 1. So as usually, please take a couple of seconds to read and understand the problem statement before we start our solution. Okay, guys, since I'm sending these problem statements to you the day before, the day prior to our discussions, let's just dive straight into our solution. So what do we have in here? We have, I believe, 3 bodies, right? We have body A, we have body B, and body C. And as you can see, they are connected with a pulley system, right? And also they told us that we know what is velocity C, and we know that it is constant, right? So let's write it down. So we know how our pulley system look like. Pulley system. And we also know that VC is constant. And they ask us to find, I think that asked us to express velocity B as a function of velocity A. And they also ask us to find acceleration B as a function of acceleration A. And that's it, yeah. This is what they ask us to find. Any questions about the problem statement? Okay, so this is how I solve it. Solution. First of all, I have a question to you guys. How many ropes do we have in the picture? I see. Sign language? Really? 1. Yes. Okay. 1 rope. Yes. Exactly. Okay. Like half of you just put 1 finger up. Yeah. So sorry. Yeah. Okay. 1 rope. Yes. Exactly. Yeah. This is the blue one. Yeah. Okay. Yeah, okay, so, and that rope is inextensible, right? So let's say that the length of that rope is constant, right? And I actually would like to express that length in more mathematical form, okay? Namely, I will divide that rope into chunks. For example, I will divide it into this, first chunk will be this blue chunk, for example, yeah? Then I think we will have this red chunk here. Okay, and also we will have these two green chunks here. Okay, and in order to express their length, I would like to include this datum. Okay, datum, and that datum is fixed. It does not move anywhere. Okay, it is always here. And I would like to use that datum to express position of block C. I would like to also express position of block B. And also, I will do the same with block A. Why not? Okay, and I think that now we are ready to write what is the actual length of that rope. So I will start, and maybe at some point you guys will help me. So I think that that blue chunk can be expressed as YA minus YC. I also think that the red chunk can be expressed as a YA minus YB. And maybe one of you, if you would like to, you don't have to, but if you would like to, maybe you can tell me what is the length of the green chunk? Yeah. And we have two of them, right? So I will multiply them by 2. Exactly. Thank you. So we will have 2 times YC minus YB. Okay, guys, let's simplify that expression. And if you simplify it, you will end up with 2YA minus 3YB plus YC. Okay, believe me that it will end up like that. Yeah, I know that you know how to do that. Yeah. Okay, guys, so this is the length of our rope expressed with these 3 variables. And this we are kind of at the displacement level, yeah, like a position level, yeah, but they ask us to go to velocity and acceleration levels. So what shall I do to this equation? Louder? Take a derivative over time, exactly. So I will take d dt, and just keep in mind that L is constant, so the left-hand side will be 0. And in here I will just have exactly the same expression, but I will just put dots above y's. So I would have 2y dot a minus 3yb dot plus yc dot. Cool. And now maybe let's express our ya dot, yb dot, and yc dot in terms of the velocities of our blocks. Okay, so by the way, I forgot about one thing. I silently assumed that this is positive direction. Okay, upwards is positive direction, yeah? And I believe that we do not know what are the velocities of blocks A and B. So let's assume that they point upwards, okay? Let's assume that they move upwards. I don't know, we'll see. VA, and so basically YA dot and YB dot will be VA and VB. And when it comes to velocity C, I believe that they told us explicitly, if you look at the picture and that blue circle, they told us explicitly that VC moves downwards, right? So I'm gonna put here minus VC. It will be negative. Okay, let's plug these values in. So this will be 0 equal to 2VA minus 3VB minus VC. And since they ask us to find VB as a function of VA, I think that you all can see the last step in this solution. Our VB will be equal to 2 divided by 3 VA minus 1/3 VC. And this is the answer A. This is clearly our answer, because this is velocity B expressed as a function of velocity A. Yeah, and VC is known. Questions? Easy so far? Yeah. Okay, so how about getting to acceleration level? What shall I do with our new equation? Yeah, over time again, yeah, d dt. And I just want to remind you guys that VC is constant. Yeah, they told us that VC is constant, so it will disappear. Yeah, so our AB will be equal to 2/3 AA. That's it. Answer AB is expressed as a function of AA. Any questions? Oh, and by the way, we can also write that AC is 0, right? Because VC is constant, yeah? So now you can see, guys, that our system is constrained, yes? Our blocks cannot move freely, yeah? They must obey these dependencies, yes? So once we define acceleration of A, acceleration of B is defined as well, yes? It must obey this rule. It will be equal to 0.667 of acceleration A. Do you see that? Yeah, they don't have like freedom to move freely, yeah? Questions? Yeah. Everything is fine? Yeah. I had a good question 2 hours ago, you know, because this is my third discussion I'm saying today. I had a great question 2 hours ago, because one person told me that this is actually not true, what I wrote in here. That blue thing is not true. And that person was right, yeah? Because I am missing this chunk here, that black chunk. Do you see that? Actually, blue length is, you don't have to write it, yeah? But that blue length is actually YA minus YC minus some constant black line, yeah? Do you see that? Yeah? Which is true, actually, yeah? So basically, I should also include that black thing in here. However, I decided to neglect it for 2 reasons. First of all, I am taking first-time derivative, yes, of that expression. And that expression is constant, yes, so it will disappear on this level, yeah? It does not matter, yeah, if it's there or not. Do you see that? Because I take first-time derivative of a constant thing. And second thing, we still model objects as particles, okay? So just imagine that block C is like very, very, very small, such that that blue line even touches the green line, okay? So that black thing is like very, very, very small, yeah, yeah. I also neglected other parts of the rope, other constant parts of the rope. Let's mark them with maybe yellow. For example, this part of the rope. Do you see that one that is around, that is wrapped around the pulley? Yeah. Can you see it, by the way? Can you see it? Yeah. 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 So I also neglected that because it's constant. Yeah. I don't have to include it in my length of the rope. Yeah. Because I know that it does not change. Yeah. Also, I neglected this part. Yeah. Because motion doesn't happen there. That part will also stay constant. Yeah, we don't have to include it in there. Yeah, just think about it at home, okay? And if you will manage to understand it, I believe. Yeah, I managed to understand it. You will manage to understand it for sure. Yeah. So anyway, in this case, we had one rope only. Yeah, but there will be problems with where you will have like 2 or 3 ropes. Yeah. So basically, you must repeat the same strategy 2 or 3 times, respectively. Yeah. For each rope separately. Yeah, and then you will just end up with these dependencies between blocks. Yeah. Okay, guys. I have a strange feeling I'm talking too fast today or too much. Is it okay? Yeah, you are with me? Yeah, thank you. So what do you think? Any questions, or are we moving forward or backwards? I don't know. Okay. So I think that officially we can say that this chapter is closed, right? Kinematics of particles is closed, but it will come back all the time, all the time. Even in this example, it will come back. Yeah. So now I would like to open a new chapter. I would like to open kinematics of particles, okay? And let's start it with brief lecture review. Let's do it? Okay. So here is my brief lecture review, and I would like to start it with one question to you, or 2 questions. Okay, so this is like 4th week of our semester, right? So we met each other like 5 times, 4 or 5 times, yeah? And the question to you is following. Have I ever used word mass in our discussions? Yeah, you don't have to remember, don't worry. No, I didn't. You don't have to remember. Have I ever used word force in our discussions? No, you still don't have to remember. I haven't, yeah. And this is all recorded. You can double check it. that I haven't used word mass, yeah. And I did it for a reason, because our previous chapter was kinematics of particles, yes? In kinematics of particles, we do not care about mass of particles. And also we don't care about the size even, it's a particle, yes? What we care about is geometry of the trajectory, yeah? We just know that our particle follows trajectory. Sometimes the trajectory is straight line, sometimes it's a curved line, yes? And then we just describe the motion using knowledge we learned during past 3 or 4 weeks. Yeah, so we don't care about mass. The only thing we care about geometry there. Geometry of trajectory. Another thing in kinematics, we do not care about the cause of the motion. Nobody tells us why the motion, what is causing the motion. Yeah, there are no forces acting on the particle. The only thing that we were told is that particle is moving and deal with it. Yes, the only thing we were said that particle is following this trajectory. We don't know why. We just know that it is following, and then we were trying to describe the motion. Yes. In this chapter, in this new chapter, kinetics of particles, we will talk about forces acting on the bodies. Yeah, and that forces will cause bodies to move, and then they will follow certain trajectories. Okay. So that's the difference. I just wanted you to see the difference between these 2 chapters. Okay. So okay, so in this chapter we will start. I will, for the first time in this semester, use the word force and mass. Okay, that would be like my introduction. Was it okay, or did I make you confused? Yeah, okay. Yeah, I don't know. I think I am making myself more confused actually. Okay, so let's draw something. Let's have a particle, and for the first time this semester, that particle has a mass. Okay, mass m. And also there is a force acting on that particle, okay? Let's say force F. And this is a net force, okay? So it's a sum of all the forces acting on the particle. Net force. So if this is the case, then I believe that I can take our particle, I can copy it here, and I also can take that vector. And I can copy it here. And if our particle has a mass, and if there is a force acting on that particle, I think that we will, the resultant acceleration of the particle will have the same direction as our force. Okay? So first thing I want to tell you guys that our force is parallel to our acceleration. okay? Or the other way around, our acceleration is parallel to our force. And they, of course, obey this expression, F equals to ma. By the way, which Newton's law is that? Second, exactly. Okay, so that's what I wanted to say. And now, from now on, I will show all the forces acting on the particle on so-called free body diagrams, okay? Free body diagram, okay? But just to save some ink, from now on, I will just write FBD instead of free body diagram, okay? And all the inertia forces I will show on kinetic diagrams. So actually in here, I will not gonna show you A, but I will show you M times A, okay? So this will be shown on kinetic diagram. Kinetic diagram. Or just to save some ink, KD, okay? All right, and the dependency between the picture on the left and picture on the right is following. F is equals to MA. That's it when it comes to my brief lecture review. Any questions? So this information that F is parallel to A and that F is equal to MA is enough to solve example number 2 actually. So what? Let's do example number 2 unless you have some questions. Okay, so example number 2. Okay, so as usually, read and understand the problem statement, please, before we start our solution. All right. So what do we have in here? First of all, we have our cart that goes up the incline, right, with acceleration AC. And we know the angle of that incline, yeah? It's 20 degrees. We know that there is a friction between mass that is placed on the cart. Yeah. So first of all, there is a mass placed on the cart, yeah, and we know that there is a friction between cart and the mass. And what do they ask us for? Okay, we will get there. But first, let's summarize our knowns. First of all, we know mass of the body. We know that mu s is 0.4. We know that mu k is 0.36. We also know the incline, which is 20 degrees. And we also know g. And they ask us to find, find the maximum acceleration such that that particle does not slip. Find max AC, so A of the cart, such that block does not slip. Okay. Okay, so in this chapter, I am actually going to sell you a recipe how to solve these problems, okay? I'm just going to sell you, I mean, if you want to buy it, of course, yeah, but I'm going to try to sell you steps you should follow, and I promise you that if you follow these steps, you will be able to solve 95% of these problems, okay? I must say 95 because I don't know what Professor Zin will come up with for the exam, yeah? Maybe he will come up with something crazy, I don't know. Yeah, but anyway, if you follow these steps, you will solve most of the problems from this chapter. In opposite to what's happening in the previous chapter, right? In the previous chapter, we were kind of like solving the problem, yeah? There was like no like steps we should follow, yeah? But in here, I usually start with free body diagram and kinetic diagram, okay? Free body diagram. and kinetic diagram. Kinetic diagram. Okay, and this will be the last time I'm gonna write free body diagram, like a full name and kinetic diagram. Okay, from now on, FBD and KD, just to speed things up. Yep. So our particle is that block, yeah? So that block is represented with a rectangle. Let me draw that rectangle. And thanks to nowadays technology, I can copy it exactly the same rectangle I can copy it here, yeah? Exactly the same rectangle will be on our kinetic diagram. Okay, on FBD, we show forces acting on the system. I'm gonna go for the easy ones, okay? So for sure there's mg. Yeah. Are there any other forces acting on the system? Anybody wanna help me? You mean inertia force, yeah? We will get there, yeah. I'm asking about forces, yeah, not acceleration. Yes, Jaden? Yeah.
Didn't you say that, like, on the free body diagram, you only show the forces, and then on the kinetic diagram, you show the mass times the forces?
Mass times acceleration.
So then, isn't g an acceleration? So why didn't you just write g instead of mg on the free body diagram?
Because this is not the acceleration of my body. This is not the result of the acceleration of my body. Okay. Olivia? Friction, yeah. And which direction it will act? It will be for sure acting along that direction, yes, but it will be pointing up or down. Up. That's your guess? That's correct guess, yes. Do you know why, or it was pure guess? Yeah. Exactly, yes. Because we want to prevent the sliding, yeah, and it will slide down, yeah. And TF, so I use TF for friction, by the way, yeah. So friction wants to prevent sliding down. Perfect, thank you. There's one more force acting on the system. Yes, sir. Perfect, yeah. I don't know your name, by the way. James, okay. And I'm Mike. Yeah, and there are no more forces. There are no more forces acting on our system, right? And now we're gonna get to what Jaden was saying. So on KD, I'm going to show inertia forces of our system, yeah? So I would like to express the motion in P and Q coordinate system, P and Q, okay? And that means that our body will accelerate, will have this acceleration, MAP, but also MAQ, MAQ. Okay, we are actually done with FBD and KD. However, we can squeeze something more from this problem because I believe that we can say something about the accelerations. Can you guys tell me what will be value of AQ? Yeah, and why? Exactly, due to the kinematic constraint, yeah, the incline, yeah? Our body follows the incline. It cannot accelerate in the direction perpendicular to the incline. Awesome, thank you guys. So this will be 0, 0 due to the incline, yeah, due to kinematic constraint. Due to kinematic constraint. Okay, and also I think that we can say something about AP, yeah? Can you tell me guys what will be the value of AP? I just want to remind you that there is no slip between cart and the block. So what will be AP? Yeah, exactly. It will be AC. Is your name Roy? Roy's my last name. Rashawn's my name. Okay, sorry. Sorry, yeah. So this is AC, sorry, a cart, yeah? Because our body has to travel with the cart. Do you see that? Yeah. So this will be due to no slip condition. No slip condition. Okay, so we are done with our FBD and KD. Second step in our recipe is equations of motion. equations of motion. These are the equations our body has to obey. Yeah, these are the equations that govern the motion. And also, this is the last time I'm going to write equations of motion. Yeah, from now on, EOM. Okay, EOM. So in here we just write sum of forces in the p direction, and we specified this direction as positive, and also we will write sum of the forces in the q direction with this direction specified as positive. Yeah, they match this coordinate system. Yeah. Okay, so what do we have? What do we have in the p direction? TF for sure, right? Yeah, TF. And I believe that there will be one component of mg acting in that direction, right? I must do some projections there. So I'm gonna do this projection and this projection, right? Here and here. And our theta of the incline will be here. So this guy will be mg cosine, and this guy will be mg sine theta. Mg sine theta. Okay, so we see that mg sine theta acts in the negative direction, yes? Mg sine theta. Okay, and this will be equal to MAP, but you guys told me that this is acceleration of the cart. This is AC. So actually we can write in here MA cart. Okay, how about Q direction? We have N acting there, and we have mg acting in the opposite direction, and this is equal to MAQ. And you guys again told me that this is equal to 0. So we can actually set it to 0. And these equations are decoupled, right? So I think that we can actually find value of the normal force acting on the system. So N will be equal to mg cosine theta. Cool. We know that this is the normal force acting on our system. But this is not what they ask us for. Yeah? They ask us to find the maximum AC. So we should have a look at the first equation more, I think. We should have a closer look at the first equation. But before having a closer look at the first equation, Mike, is yours. Are we on the same page? Yeah? Any questions? Okay, so let's see what we have in here. So we have TF minus mg sine theta, and this is equal to MAC. Let's see. So first of all, we have one equation, right? This equation. Because the other one is solved, yeah, the blue one is solved. Let's forget about it for a second, yeah? How many unknowns do we have? I bet that our TF is not known. We don't know the friction force. And unfortunately, we also don't know the acceleration of the cart, yeah, because they ask us to find it, yeah. So it's not good. We have one equation and two unknowns. Unsolvable. Yeah, we cannot solve it. We must have exactly the same number of equations and unknowns in order to be able to solve it, right? So we should find one extra equation, yeah. Any ideas? Any propositions? Sean? Yeah, we can go for the friction law. Yeah, exactly. Thank you. Yeah, we can't do that. Let's try. Maybe it will work. We will see. I don't know. So we have static friction case. Yeah, because they ask us to do something to prevent slip. Yeah. So we won't have kinetic friction. Yeah, we will have static friction. Static friction case. Friction case. And in this case, I think that our friction is lower equal mu Sn, right? And I watched yesterday's lecture. Professor Zin spent some time of the lecture on explaining that inequality, I believe, yeah? Okay. And we can actually say more, because they told us that they would like to find maximum acceleration so that that block does not slip. So I believe that we should actually go to this specific case, that right before before sliding, our TF will have maximum value, which is equal to mu Sn. Yep. So actually our TF will have this expression, mu S, and exactly what Sean said. I'm going to plug this N in here, mg cosine theta. So this is our expression for TF. Okay, thanks guys. We found the second equation, yeah? Now we have two equations and two unknowns, yeah? And I'm going to plug one of them in here. And we can solve the problem. So in here we will have mu S mg cosine theta minus mg sine theta, and this is equal to m AC. I believe that these m's cancel out, and we ended up with AC equal to g times mu S cosine theta minus sine theta. Let's plug in values. AC, it will be AC max, I believe, right? So I can put even max superscript in here. Max. So this will be g times 0.4 cosine 20 degrees minus sine 20 degrees. And if you grab your calculators, you will end up with AC max equal to approximately 0.332 meters per second square. Or if you prefer US units, AC max will be equal to approximately 1.090 feet per second square. Oh, sorry. So this is our answer. Okay, so if our cart travels with acceleration larger than this one, the block on top of it will start sliding, yes, downwards. And if the acceleration of that cart is slower, is smaller than this value we obtained, the particle will travel together with the cart. That's it. Mike, is yours. How does it look like from your perspective? Is it digestible? Yeah. Questions? Okay, so keep in mind that recipe, okay? It will come back like 700 times this semester, okay? So first of all, free body diagram, then equations of motion, then count number of equations and number of unknowns. Unfortunately, usually we'll end up with more unknowns than equations, and you will have to look for more equations, yes? And once you have exactly the same number of equations and unknowns, then dynamics stop and mathematics starts. Yeah, then you have to solve them, yeah. So again, FBD, EOM, then count number of equations and number of unknowns. You will have more unknowns than equations. Look for more equations and solve it. Okay, I will write it down in the future, okay, on the board. So this is your take-home message, and I would recommend you to take this recipe and tackle homework problems with them, okay, with it, yeah? And I promise you that you will destroy every single homework problem if you follow that recipe, yeah? So it looks like one evening and you're done with homework, yeah? Yeah. He was first, Nathan, yeah? Jaden?
I'm just kind of confused on like how you know what to put on your kinetic diagram. You said it's because you don't show gravity y, but you show normal force in the kinetic diagram.
In the kinetic diagram,
yeah.
I don't show normal force.
Well, whatever the vector is that's pointing in the same direction.
Oh, listen.
What's the criteria for if something is put on your kinetic diagram?
Sure. So actually, let me tell you what's going on in here. So I do not know which direction my body will accelerate, okay? So actually, I assumed this direction, M, A. I don't know which direction will it accelerate, do you see? And then I decided to express my motion in this coordinate system. That's why I projected this black vector on these two directions. Do you see?
Okay, so those are just components.
These are just components, yes. And during our solution process, we ended up with one of them being 0 and the other one not being 0. Yeah.
Because it's all parallel with the ramp.
Yes. Yeah.
That
Yeah.
makes sense.
Yeah. If you want, you can solve this problem in this coordinate system. X and Y. Yeah. Odd, good, civilized X and Y. Yeah. Then you will have to project. Then your kinetic diagram would look like that. MAX, MAY. But I thought that there's no need for that. Yeah. I found the previous coordinate system much easier and much more comfortable to solve our problem.
Okay, makes sense.
That's a good question. Yeah. Yeah, Nathan.
So is that MAQ or that AQ always will be 0?
If you follow the straight line, yes.
Is there any like cases where it won't be 0?
Yes, if you don't follow if you have a curvature like that.
Can you not solve it then?
I can, and you can as well. On Friday and on Wednesday we'll solve such cases, yes. Yeah. Yeah. And you know exactly what it will look like. Then acceleration will be we will express the motion in normal tangential coordinate system. And we will equal our accelerations to those components of normal tangential or polar coordinate systems, yeah? Can you wait 2 more days?
I will wait.
Okay, thank you. Thank you. Good. Hey, cool. Thank you, guys. I like those questions. Okay. Any other questions? So actually, we are done with this discussion, yeah? So, I don't know, what time is it? You have 7 more minutes. Do you want to do quiz number 1? So, I don't know, you don't have to familiarize yourself with the problem statement, yeah? Because you already seen it. Okay, so, but for those of you who are watching this video on YouTube, feel free to pause the video right now and read and understand the problem statement before we start our solution. All right, and here is my solution. Well, this quiz is related to the previous topic, right? The kinematics, yes? So as you can see, we don't tell you what is the mass of the body, yeah? We just know that that body is moving, and that's all, yeah? And this is the trajectory, by the way. Our trajectory has such geometry. Trajectory. And in order to solve that problem, I would like to divide this trajectory into 2 chunks. First chunk is from A to B. Yeah, it's just a free fall. Yeah, our body follows a straight line. And then second chunk is curvilinear motion, right? From point B to point C. Okay, so I would solve that problem like that. And what is the initial velocity? I think it's 0, yeah, because our body is released from rest. So our V0 is 0. Yeah. Okay, so this is my solution. And what they ask us to find? They ask us to find acceleration at point C, so at this point. Yeah, so we need to know AC at this point. Okay, so this is my solution. First part is motion between A and B. So in this case, I believe that we have acceleration equal to minus g, right? And it acts downwards, yeah? And this is constant. And I would like to end up with velocity at point B. So which definition for acceleration I should go for? I think that, do we know how much time does it take to reach point B? We don't know how much time it takes, yeah? We just know the distance, yeah? We know h. So I think that this definition will be useless. dv dt. So this is useless for us, right? Yeah, so that's why I'm going to go for this definition. A is equal to V dV ds. Okay, so we will end up with V dV that is equal to A ds. But A, we know, it's minus G. Okay, let's integrate. So I believe that we will start with velocity 0, yeah, and we'll end up with VB, yeah, velocity at point B. And let me introduce datum here. This is our datum. Okay, so I believe that our motion starts at position H and it ends up at 0. So if I integrate that, I will end up with 1/2 VB squared, and this is equal to minus GS from H to 0, right? So this will be equal to just GH, right? So from here, you guys can see that our VB is equal to square root of 2GH. Yep, and if you plug in values, you will see that this is equal to approximately 14.007 meters per second. Cool. We are done with motion from A to B. And we ended up with this blue vector of velocity. Our velocity points downwards. Yes? I hope you can see it. Yes, and this is magnitude of our velocity. Yeah? This is magnitude of our blue vector. Questions? Good? Okay, so now chunk BC. Now between BC. And I believe that this will be curvilinear motion, right? Let me copy it here. So yeah, clearly our BC trajectory is a circle, yeah? So that will be curvilinear motion. So we have choice. We can go either for normal tangential coordinate system or polar coordinate system. I'm going to go for normal tangential, okay? So, and they ask us to find acceleration at C. So our A, in this case, will be equal to V dot ut plus V squared rho un, okay? So what we have to find these two values, AT and AN. Let's start with AT. So AT will be tangential component, right? So it will be along this unit vector, yes? This guy will be here, okay? This is UT. And UN will be pointing towards the circle. Can you see them? So I believe that they gave us expression for AT, right? Because they told us, if I scroll up the board, that our particle decelerates, yes, along the curve, yes, and it decelerates in this fashion, yeah. So I can write that our AT is actually minus AB, minus 4S, right? So now the only thing to find AT at this green point, yeah, is to replace S with this arc length, yeah. So what would be that arc length? This would be rho theta, yeah, and theta is 45 degrees, yeah. So it will be pi over 4. So this will be minus 4 times r times pi over 4. So this will be 4 pi, yeah, because r is 4 meters. 4 pi, and if we grab our calculators, this would be 12.56 meters per second square. Awesome. So we found this value. Yeah, we found this value. So basically we can write that our A at point C is equal to, I forgot about negative sign, right? Negative here. So this will be minus 12.56 UT plus something UN. Yeah, and the rest of the discussion I will spend on finding this something, okay? And that something is AN. And this is equal to V squared rho. But rho is constant, yeah, because it's a circle. Yeah, so rho will be R. And now I just have to find V at point C, yeah, at this black point. Yeah, if I find velocity at this point C and I square it, I can go home. Yeah, let's do it. So I think that I would like to do it in a following way. I know that our AT is minus 4s. So again, this is not a function of time, it's a function of position, yes? So I'm gonna go for this definition, V dV ds. Okay, and I can do V dV, and this is equal to minus 4s ds. Let's integrate. What were the integration bounds? So I think that our velocity at the beginning was at this point, I think it was 14.007. Yep. And we'll end up with some velocity at point C. And the arc starts at B and ends at R 45 degrees. Yeah. R pi over 4. So this will be 1/2 VC squared minus 1/2 14.007 squared, and this is equal to minus 4 times 1/2 R squared pi squared 4 squared. Right? I believe that we can get rid of these halves, and we just ended up with expression for VC squared, which will be 14.007 squared minus 4r squared p squared 4 squared. If you grab your calculators, you will end up with VC squared equal to 15, let me double check, 156.7 meters squared second squared. And if I plug it here, 156.7 divided by 4, I will end up with 39.2. Yes, 0.2 meters second square. Okay, so basically that missing thing was 39.2 meters second square, and this is the answer. Okay, guys, that's all I prepared for today. Are there any questions? Yes, Jackie? Yes, you can. Yeah. Jackie, it's already 10:45. I must finish, but I can stay for five more minutes and we can talk, okay? So thank you, everybody, and see you on Friday. Bye.